Today we're going to talk about the refrigeration cycle. We're going to talk a little bit about the refrigeration circuit, the different components that are within the circuit, and we're going to talk a little bit about how the different components function. We're going to talk about pressure temperature charts. We're going to talk about the relationship between refrigerant pressures and the refrigerant temperatures, and we're going to discuss some of the different actual superheat and subcooling categories of the circuit itself. The first thing we're going to talk about are the components in the refrigeration circuit. So we'll start over here with number one. And the number one, this is a drawing of a compressor. The compressor's purpose is to move the refrigerant through the circuit. So as you can see, there's red arrows over here, and then we go through this different refrigeration circuit. It travels all the way through the blue arrows and comes back to the compressor. There's two line sets that go into the compressor. We refer to the refrigerant entering the compressor. The line set would be called the suction line. Anything coming out of it would be the discharge line, or it could also be considered the hot gas line. Right? The next component that we're going to talk about would be the condenser. The condenser's purpose is to take that really hot vapor, change that state or condense it to cool it off, reject the heat out to the outside air, and cool that refrigerant all the way down to a liquid state. All right? And we'll discuss this in detail here in a few slides. The next component would be the metering device. And the metering device's purpose is to take this really high pressure liquid and to kind of push it into a smaller orifice and lower the pressure for the evaporator to handle. So there's liquid going into the metering device and liquid coming out of the metering device, but the change of pressure within that metering device is what really makes the circuit function the way it does. All right? And the last component would be the evaporator. And the evaporator's purpose is to absorb heat in a conditioned space and reject it into, or absorb it into the refrigerant and eject it out into the atmosphere or into the air, right? So we want to get that heat out of the conditioned space. So we're going to discuss some of these functions here in a second. But the first thing I want to talk about after the components in a refrigeration circuit would be the relationship between pressure and temperature. Pressure and temperatures are very important when it comes to air conditioning. When we're talking about air conditioning, if we didn't have refrigerants, we wouldn't really have air conditioning. You could take water and run it through a compressor, and you could run it through a condenser, and you could run it through a metering device, and you could run it through an evaporator, but it wouldn't function very well. It just doesn't have that capability. The efficiency just isn't there. So we came out with these new things called refrigerants, and the refrigerants are special because they have saturation or boiling temperatures that are really low. So they change the state of that refrigerant at a very low temperature, which increases the amount of heat that we can absorb into it and reject out of it. So a couple of things I want to point out to you. This over here is called a PT chart, or a pressure temperature table. All right? And these are really important to us as service technicians and installers because we have to really understand what's happening inside a refrigerant circuit that's completely closed off. We can't see the refrigerant flowing through the circuit for the most part. And so we have to kind of get temperatures and pressures throughout the entire system in order to really get a good view inside of the system. So let me break down some of the components first. And at the very top of this table, they're talking about high pressure refrigerant. And high pressure refrigerant are refrigerants like R22, 410A, 407C. These are kind of common refrigerants. And what they mean by a high pressure refrigerant is basically this. It has a pressure of 155 degree or psi to 340 psi at 104 degrees, right? So that's that classification. And they have several different ones. They have low pressure, medium pressure, high pressure like we're seeing here, and then very high pressure over here, which would be CO2. The next line down, and a lot of your phone apps with pressure temperature charts don't have this on there, so this is a good thing to cover in this section. ASHRAE classifies refrigerants, and they have been for a few years now. And what they do is they classify the toxicity level and the flammability level of that refrigerant. So as an example, we'll go to R22 because R22 is a really common refrigerant, especially in comfort cooling. So R22, according to the ASHRAE classification, is an A1, and you can see this up here in this gray area. So what ASHRAE says is that A means that it is a low toxicity level, and 1 means that it has a low flammability level. All right. So when we're dealing with R22, what ASHRAE is saying is that we, as service technicians and installers, we can work with this stuff on a daily basis and not have to worry about the toxicity levels to us. All right. They're not saying you can run off and huff a tank of gas and R22 and be okay. That's not what they're saying at all. What they're saying is that we can work with this, and there's a low chance of us ever having anything happen to us because of that, okay, as far as diseases are concerned. The 1 means that it's low flammability. So the 1 means that if it's exposed to flame, it's probably not going to spread, fire. If you look over here, and we won't discuss this too much, but there's these hydrocarbons. Hydrocarbons contain flammable refrigerants, okay? So they are considered low toxicity, which is the A, but they have a high flammability, which is the 3. So they will catch fire if there is a torch or something involved. All right. The next line down, this GWP number, this is also a good number. Several years ago, when the Montreal Protocol came out, they realized that some of the refrigerants that we were using, like R11, R12, were really harmful to our stratosphere. And they had this ozone depletion problem, and we ate a hole in our ozone above Antarctica, and this was a huge problem. And so the world came up with this Montreal Protocol, and then more specifically within the United States, we came out with the Clean Air Act. And the Clean Air Act basically is a set of rules or laws that we have to follow in the EPA guidelines in order to make sure that we do not use refrigerants that are, or release refrigerants illegally that are going to be harmful to the stratosphere. Now that has nothing to do with this global warming potential, this GWP. The GWP is something completely different. So the ozone depletion potential is also a number, and that means that the certain refrigerant is going to go up in the stratosphere and tear apart our ozone layer and create havoc in our ozone. The global warming potential is also a bad thing, but it affects our atmosphere more like a mirror, right? So as the sunshine comes through our atmosphere, it bounces off the earth, and then it goes up and reflects off of these refrigerant particles that are staying up in the atmosphere and coming back down and creating a climate change. So GWP is a pretty high concern nowadays. So as we're looking at R22, you'll notice that the GWP is 1810. That's really, really high. Some of the other refrigerants that we use commonly might be 410A. So I'm going to go over here and kind of highlight that. 410A is a very common refrigerant that we use nowadays, whether it's in residential, commercial, whatever it is, we use 410A a lot. It's a very efficient refrigerant, and it works really, really well, but it has a really high global warming potential. So the global warming potential for 410A and R22, what they're saying is it's too high. All right. So we have to pay attention to these numbers, and what I'm going to say, and this is where I'll stop, is that we will start seeing a large and fast change in the HVAC world just because our refrigerants aren't working correctly for the atmosphere. They're not healthy for the earth. Okay. So we're going to start seeing a lot of different refrigerants out there, and it is important that we keep up to date on that. All right. So we have to understand what they are and how they work. So let's go back down here, and this is the more common part of the pressure temperature table that we're used to. And we'll just take R22 for an example. And if I have a known temperature, I also have a known pressure. It just goes hand in hand. They correlate together. There is no changing that. All right. So let's take, for example, that I have a temperature of 45 degrees. That's this line right here. So at 45 degrees, what this table is telling me is that pressure within that R22, that refrigerant pressure, is going to be 76.1 psig. All right. So at 76.1 psig, I have a known temperature of 45 degrees. As a slight example, just to make this easier, if you are working on an evaporator and you happen to know that line on your evaporator, you're taking the temperature reading on that, and it says 45 degrees, that means that the pressure right there where you're taking the temperature is going to be 76.1 psi. You don't even have to have gauges hooked up to it to know that. All right. Now, we'll discuss a little bit more saturation temperatures, and we'll talk about superheat and subcooling and how that affects a system in a few slides. All right. The next thing I want to cover are some basic definitions, and the definitions are important to understand. So the first one I want you guys to understand is sensible heat. Sensible heat is a fairly common sense approach to heat. It's something that we can feel. So the definition says heat energy that can be measured by a thermometer or sensed by touch. So what they mean by that is if I walk up to my stove and it's on and I put my hand on that stove, I will know that it's hot, right? That is a sensible heat. That is something I can feel, I can sense. If I walk up to my thermostat and it says 72 degrees on it, then that is a sensible measurement of the heat within my house. All right. So that one's pretty easy to understand. The next term is a little bit more difficult. It's called latent heat. And latent heat, the definition is the heat energy absorbed or rejected when a substance is in the process of changing states. All right. And the easiest way for me to explain that is with water. All right. So water can exist in a solid state, a liquid state, or a gaseous state or vapor, right? So the solid state would be ice, liquid would be just water that we have in a cup or a bucket, and then gas would be steam, right? So the latent heat is the energy that it takes for that substance to change from solid to liquid or from liquid to gas or vapor, right? So melting a block of ice or steaming a pot of boiling water, something like that. That is latent heat. And then the last one I want to kind of cover real quick before we get into too deep is the saturation temperature. The saturation temperature is a temperature where liquid and vapor refrigerant both exist. That saturation temperature was exactly what I was showing you on the pressure temperature chart. So if it was 40 degrees and it said 76.1 psi, that is your saturation temperature of the refrigerant. That's where it's changing states, right? And it could be a mixture of both at the saturation temperature, okay? The next thing I want to kind of talk about with you guys is the evaporator and how the evaporator functions. So the evaporator is where we add heat to the refrigerant. We start adding heat to the refrigerant through the fan, right? So we're going to take this warm air from our building and we're going to blow it across this coil, and it's going to start heating up the refrigerant that's flowing through this line set right here. And as we do that, as we heat that refrigerant, we will see that refrigerant not only changes pressure, but it also changes temperature. And as it changes temperature, it's actually going to reach a point called the saturation point. So let's go ahead and bring that up. If you look at this line right here, it says that the saturation point is basically right here in the center or close to it of the evaporator. So as the refrigerant comes into the evaporator, it's flowing as a liquid, and as that air blows across that liquid and it's warm, it warms up the liquid and starts changing the state. As it changes the state, it hits the saturation point, which is the point of no return, where it starts turning in fully into a vapor. Once we get to the full vapor, about right here in our evaporator coil, it will actually start absorbing more heat. And any heat added above the saturation point in the evaporator is considered superheat. Superheat is a really important thing to understand. Superheat is how our compressors are protected in the system. So let me explain this a little bit further. So I have this gas or this vapor or this refrigerant going out, and this line set might be kind of cold, but it's still a gaseous state. And it's a superheated vapor, so we've added extra heat to this, and it keeps coming up through the suction line and it enters into the compressor. The compressor itself as a device can only compress vapor. It's only built strong enough to compress vapor. Liquid is very dense and it's very difficult to compress. And our compressors in the HVAC world aren't built strong enough for that. So we're only built strong enough to compress vapor. So that's what we need to ensure that comes in. The only way to ensure that we have vapor is to make sure that we're changing the state of the refrigerant down here and adding extra heat up here so that by the time it gets to the compressor, it is a superheated vapor and the compressor's good. If for whatever reason we didn't hit our saturation point until this point in our line set or this point in our line set, we potentially could have a mixture of liquid and vapor going into the compressor, and the term for that is called slugging. Slugging is very difficult on a compressor. It will really tear it up. It could remove some of the oil, it could put different pressures on the system, and it could break the compressor mechanically. Another problem with that is if we had full liquid going into the compressor, it's called washing the compressor, and we actually wash all of the oil out of the compressor immediately, and then we don't have any lubrication within that motor and those pistons and those components, the mechanical components in the compressor. So that's very difficult on a compressor too, and it will probably break the compressor very quickly. Moving forward, I want to kind of explain the latent changes, right? So this chart right here is a nice chart, and it'll explain how water changes, all right? So at this point down here, what we're saying is we have a big block of ice, all right? And I start adding heat, and what they're showing you guys down here is the BTU ranges, okay? So these are British thermal units. This is the amount of heat we're adding to the system, all right? So at this point right here, I have a block of ice, and I start adding heat to it, all right? And you guys could assume that it's probably 32 degrees Fahrenheit, okay, at atmospheric pressure. What we're saying that we start melting this block of ice continually by adding more and more heat, but at this point over here where we're not quite fully changed into liquid water, we are still at 32 degrees Fahrenheit. And I know that's a hard concept to imagine. We start here at 32 degrees Fahrenheit, we add heat, so automatically we would assume that we have more heat over here, or a higher temperature. But this is a latent change, and we cannot perform sensible heat change when there is a latent change going on in the system. So here is 32 degrees, here is 32 degrees. After this point, we turn into full liquid water, and any heat added above that is a sensible change because we haven't changed into a vapor yet. So we start adding more heat from 160 to 340 BTUs. We create more heat and that temperature rises, and that's a sensible change. We'll actually be able to see that, sense that, feel that, and read it, okay? And it'll increase that temperature all the way up to 212 degrees at this point right here. And we're assuming that this is at atmospheric pressure. So at 212 degrees atmospheric pressure, we all know that we start boiling water, we start creating steam. That is another change of state. That's a latent change. So we're changing from liquid down here, bring the temperature up to 212 degrees, and we still increase our temperature, but it's a latent change. We have to create steam. We have to change that state of the water. So down here you can notice we have 340 BTUs all the way up to 1310 BTUs. So we're using a lot of energy down here to change the state of this liquid water into steam, all right? And that's latent. It's a lot of energy that we have to use to change that. Anything above that point, above that, is going to be hotter than 212 degrees, and it will be pure vapor steam. There will be no liquid left at all, all right? When we're talking about the condenser is basically the opposite of a evaporator. So we come out of the compressor as a superheated vapor, and it discharges through the discharge line into the condenser, and it comes in as a gas or a vapor. And as the air flows across that coil and it starts to pull some of the heat away from that out into the ambient air, the outdoor air, it starts to change the state of the refrigerant back, right? And so what we're looking at here is we start cooling this refrigerant, this gas, this vapor, and it starts to hit a point that would be called the saturation point again. And that's where we have both vapor and liquid in the same area, okay? So we change that state and it starts to drop down in temperature more, and that refrigerant changes all the way back to a liquid. And when we come out of the condenser, we keep rejecting heat throughout this whole second part of the condenser, and it becomes subcooled. So this is a subcooled liquid. Now, if anybody's ever touched or measured that liquid line coming out of the condenser, you will know that that is extremely hot. It's a very high temperature. You'll burn yourself. You'll regret that you touched that line set. So you're thinking the term subcooled doesn't make much sense. But the temperature up here is way hotter than the temperature down here. And we have already created the change of state in the refrigerant. We've passed that saturation point right here. So therefore, anything below the saturation point in a condenser is considered subcooling. All right. So we come out of the condenser as a liquid and we flow into the metering device. And we'll talk about the metering device in a minute. The next thing I want to kind of show you is the reverse cycle on this exact same chart. So I'm up here and I'm in a gas, right? I'm in that really hot gaseous state. I'm superheated, okay? And I enter into that condenser coil per se, right? Even though this is water, and we're running in there and we're rejecting some of the heat, and we're rejecting the heat. And as we come down, we start condensing the temperature. We start condensing that refrigerant, or in this case, it's water, and we're rejecting that heat. So at this point, we're starting to do that latent change, only in reverse. And so as we bring that latent change down and we start to change the state of that refrigerant, that medium, right? In this case, it's water. We will hit a point of 212 degrees, and anything below that, right? We've already changed our state. We've hit that saturation point. Anything below that becomes subcooling. So we're going to subcool, and subcooling happens to be a sensible change, right? It's a sensible measurement. We can read that. So subcooling comes down here, and then we hit another point where we start to reject even more heat, but we're starting to, in this particular case, turn this water into ice, okay? And so that's a latent change of state. We need to change that state. So as we're rejecting that heat, rejecting that heat, rejecting that heat, it's all latent and we won't see any sensible change. And then anything past this complete latent change will be all subcooling again, okay? One of the last things I want to talk about is the metering device. And I'm going to specifically talk about a TXV because TXVs are more common in the commercial refrigeration world than they would be maybe in other areas. So in our world, the TXV is a valve. It's a metering device. And you have an inlet and an outlet. And so the inlet comes from the condenser. So we have a high pressure liquid entering into the TXV on this line set right here. And then we have the exiting liquid refrigerant. It's a lower pressure refrigerant coming out and feeding the evaporator coil with liquid refrigerant. Down here, you will notice there's a spring adjustment, and it even says superheat set point. I want you guys to ignore that for a second. There's a spring that's located in here, and up here, there's a diaphragm that moves, all right? Coming on top of the diaphragm, there's a capillary tube, or really small copper tube, and a bulb. And inside this bulb contains refrigerant or gas or a mixture of both. And when that refrigerant warms up, it expands. And by expanding, it pushes pressure down here, pushes against this diaphragm, and allows this to push against the spring. So this opens up this valve in here and allows more refrigerant to flow through. If it cools off, it will reduce the pressure on here, it'll reduce the pressure on the diaphragm, and it'll allow that spring to overcome that diaphragm and push up, and it'll start to reduce the amount of refrigerant flowing through here, okay? All TXVs have an equalization line. Some are internal and you'll never see them. They're just a separate port that's kind of drilled into the body of it itself, and it allows for equalization within the valve itself. This allows the valve to work more efficiently, and it also allows the spring to push back and forth a little bit easier. Okay, some TXVs will have an external equalization, so there will actually be a port that comes out and goes down here into the suction line. You'll find those types mostly in systems like variable refrigerant flows that have multiple evaporators on them, maybe. So they'll have multiple heads on one condenser. So there's going to be different loads on different evaporators. So it makes it a little bit easier on the TXV to equalize that, or not to equalize, sorry, to feed the right refrigerant to the right evaporator. Okay. So that's TXV. The compressor, and we already talked about this, the only job that we're going to really talk about right now for the compressor is it kind of has two parts. The compressor moves things kind of like a pump does in a water system, right? It's going to move the refrigerant through the system, and it's also going to provide a pressure differential in the system, and that helps to change the state of the refrigerant, okay? So it's going to push that through the TXV really, really hard. If we didn't have the compressor, the refrigerant would just sit still. So it needs to move, and it needs to change pressures in order to adjust in the condenser and adjust in the evaporator to the loads that we have. So we're going to discuss different types of compressors in another video. I kind of ran over on this one, so I apologize, but I want you guys to get the gist of the refrigeration cycle. So thank you very much.